Hello, my name's Brandon. I'm a staff engineer at Dark Matter Technologies, and as well, I am doing my master's in computer science. And for one of my classes in the computer science program, I was asked to build a load balancer for the final project. And so I started to research different projects out there and people building, and there's a ton of resources, a lot of really good resources too for what load balancers are, how they work, and whatnot. But what I found was there wasn't a lot of resources for, like, hey, I'm building a load balancer. So, hey, I built a load balancer. And to start, so I want to talk it through, and it's available on GitHub, so feel free to check out the repo. But before talking it through, I want to talk about some of the constraints. And I'm not going to go into a lot of detail about all the different algorithms for load balancers and whatnot. Again, if you want to check those out, there is a lot of awesome resources on YouTube and beyond to just talk through those things. So if you want to start there, you're more than welcome. But to jump in, I will give a very high level. So the very high level is, let's say you have a website as an example. And then the website, the user goes to make a call to get some data. And when they go to get that data, let's say they're going over to this server. Then this server has the API on it, has the database on it, whatever it is. And the server itself starts to build up a lot of traffic. More and more people get this website. It's getting very popular. And all of a sudden, we're starting to see some issues with performance, with the server slowing down and whatnot. So the solution to this, instead of just scaling up with bigger server and adding RAM until the end of the day, the solution is one solution is to add a load balancer. Now, a large part of what a load balancer does, and the part that we're going to be focusing on, is distribution. So what we can do now is we can add more servers, and you can add as many servers as you want here. And the load balancer then, its job in this scenario is to determine which server I need to send the next request to. So a user sends a request, and that request goes to this one, or does it go to this one, or this one, etc. And so how it determines which server to send it to next is best is where all these different algorithms come in. So the algorithms have different approaches to solve this problem. And there are a lot of them out there. You can look them up. What I wanted to do is to be able to demonstrate some of those algorithms in a way where we can see that traffic and visualize what this means within the context of my local system. Being that it's my local system, there are some constraints, and we're going to be talking through those. There are typically two types of load balancers, depending on how you define them, which is dynamic and static. So for the most part, we are going to focus on the static algorithmic approach. Because the dynamic algorithms, like an example would be CPU usage. So it's going to look out and see what the actual usage on the server is, and then distribute the request to the CPU with the lowest amount of usage. If all of these are running on the same CPU, which they are for this example, does that make any sense? No. So it doesn't make sense for me to have that. So this isn't a production scale type thing. This is really for educational purposes. So moving over to the actual diagram that reflects my project here, I called it the dynamic load balancer, and we'll see why in a second. So we have the web tier, and like we just explained a minute ago, the web tier calls over to the load balancer, and the load balancer, depending on what algorithm is configured, will decide which server to send the request to. So in the case of, we'll use as an example, round robin. Round robin is a static algorithm. And all round robin is is it makes its rounds. So it'll go here, then it'll go here, then it'll go here, 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 and then go back up here, and then continue on. And it goes around and around and around, and it ends up in an even distribution. That is quite nice in many cases. But it's not perfect for all cases. We'll explain that later. What was fun for this, what makes this a little bit different, is I added this little arm here, which is I wanted to make it a dynamic load balancer, and what I mean by that is I made the ability for the user to configure which load balancing algorithm we're going to use. And because of that, we can kind of track the performance around the different algorithms and how they're doing. So let's go over to the UI. In the UI, it's fairly simple. There are 3 sections: server configuration, batch request configuration, and transaction history. So let's start by configuring our server to the algorithm we want. So we're going to make it a round robin. That, if you remember, based on the diagram, it takes 30 seconds to update, so we're going to wait 30 seconds as it does that. As that's going, let's talk about batch request configuration. So when we're sending this from the local, we need to send the request in batches very, very fast, so the actual backend, the API gets enough distribution to make something meaningful of this project. So we have different batch sizes all the way up to 1,000. And there's the button use load balancer or not using the load balancer. The reason this is here is so that we can actually track the performance of how is the load balancer doing. Now, fast forward, there is a constraint around this that I had to do artificially. And if I was to go to the constraint just very quickly, on a side note, the constraint is that I have a max concurrent of 5. So in any system, a server can only handle so many requests. And at some point, it can't handle any more requests. So to kind of mimic that in a small scale, I made the single server running have a max concurrent of 5 at a time. That way we can see the need for a distribution. So even in 30, we can see some type of performance gain because of that constraint that I put. When the use load balancer is off, all that is happening is the web tier, instead of going to the load balancer, goes directly to 3001. And this is available on GitHub, so you can see that code. It's very clear that this is what's going on in the background. I'm not going to dive into every line of code. So for now, let's run 30. So we're going to use the load balancer. We have our request group ID, which all this request group ID is it tracks into the database so that I can group all of the requests together. So I have this transaction history with just a few things on it to tell me which algorithm was used, which server it was processed in, was this synchronous. It lets us get some data. But most importantly for us right now is it allows us to group it. What we can do with this is we can then take this request group ID and visualize what happened. We can see literally where every request went, which server or port in our case it went to. Now, if you remember how I explained round robin a second ago, it doesn't quite look like that. It's really close, but you can see every once in a while, one of these requests are off. So each of these represent one of the servers, right? And you can see them filling up the buckets. I'll replay it there. And this one is out of order. The reason for that is because it sends so fast using Angular's fork join that when it gets to the server and the API itself makes the DB call, that timestamp might be out of order. It might have actually processed these out of order with how fast it actually went back there. So to ensure that we could show a perfect synchronous system where you can see that algorithm exactly how you would see it in your textbook, let's say, I added this send synchronous. So instead of using fork join and sending them all concurrently, we are going to send them synchronously. It happens in a for loop with a little awaiting for each one. And it takes a little bit more time. You can see it's taking time. And even with 30, it took a little bit of time. But now what we have is a perfect round robin. And you'll notice a couple things as it's going through. Our little buckets are filling up. And they will all have exactly 6 requests. They all happen linearly following the round robin, and we can visualize that in many ways. We can download the CSV results, all that fun stuff. Now let's just do one more algorithm. We'll do weighted round robin. So weighted round robin is a little bit different, and weighted round robin, you may have a server that you want to take priority. Like maybe you just have this server set up. It's the best server in the entire planet, and this thing needs to handle 90% of your request, or even just 30% of your request, whatever it is. For some reason, you want to distribute against round robin, but you don't want it to be perfectly equal between the servers. You could use something like weighted round robin. And in a weighted round robin scenario, let's do that. View transaction. What we'll see is the way it's configured in the back end, 3 goes to this, 2 goes to this, 2 goes to this, 1, 1. So it's 3 times as many requests, 2 times as many requests, 2 times as many requests, and then request. We'll show that in a couple minutes here. Just to fast forward a little bit here, I'm going to do the other 2 algorithms as well. So we'll do the random algorithm, and then after we do the random, we will do the least connections. So to talk about the random just for a second, it's exactly what it sounds like. The random algorithm is it picks a random number. You have the different ports we have there, and it picks a random port, and it sends it there. This actually can be quite nice. In round robin, you'll see in the code that we have to use locks to ensure that the next port chosen is the next port, that we're not serving up 2 of the same ports at the same time to 2 different processes, if you follow that. But random doesn't care. It doesn't care about locks. It's just, here's a random number, and okay, run it on that one. And so I can take this and then go ahead and view the transaction history. And it is very random. And when we look at the outcome, let's see what the outcome was. 75774. So fairly evenly distributed. If we used a larger size sample, it might be closer, in theory at least. Let's swap over to least connections now. So the least connections algorithm, what that one does is that one is typically considered more of a dynamic one, but we can still use it in this case at least a little bit. Least connections is going to it's going to maintain how many connections to each server are running, how many concurrent connections, and then it's going to manage those connections and see who we ought to serve the next one to. So if something has really long running processes and then some of the processes are really short, it gives us the benefit of being able to choose whichever one has the least amount of connections. So in a service like round robin that could flood it, where it keeps going around and around and around, but the big process, for some reason, we're just getting unlucky, keeps ending up on the same server, and now this one server is getting kind of bloated in terms of the load. The least connections is going to manage that. It's going to be mindful of how many connections are actively concurrently working so that we're not overloading any single server. Let's go ahead and check out what that looks like here. So if we see in our case, it almost looks like a weighted round robin in a sense. You have a lot of times you'll see 2 fire at the same time to the first server, and then it continues on. And the reason for that programmatically, as we'll see, has to do with how fast these are firing and how fast they're being processed. So since it's looping through, if you can visualize in your mind, the code's coming up in the future. It's going to be looping through, and since it's looping through and checking for least connections, and it's checking this one first every time, it's going to give this one the request first if it's already ready to go. So most of the time it's going to be this, since the request load itself is so small. And last thing I want to show here before moving on is just the overall performance. The overall performance here, what I've done is I just took an accumulative, all of the data that I've had while testing this and whatnot, and made a little view around it. In this view, you have this view as well. If you pull down the repo, in the create database, I have the performance results view here. All it's going to do is run a little diff to see what our results are compared to the single server. So load balancer versus single server. So if I click it, I can see that we are 34% faster with the load balancer than with the single server. Keep in mind, again, there are some artificial constraints put in place since everything's happening on the same server, but hopefully you can get the idea. I do have the show synchronous button here as well, because it felt like I had to show those since I had the data, but since it's synchronous, it doesn't. Synchronous kind of defeats the purpose of this. The only reason synchronous is here is so that you can demonstrate algorithms kind of perfectly in a textbook fashion of how it's supposed to distribute in a scenario like round robin. Okay, let's go to the code. So just two parts very simply. I'm going to skip the UI entirely talking about it since that's not the focus. And I'm going to skip the API for the most part, but I do want to mention it. What I want to mention in the AI is when I look at the routes here, this is just a little Nodejs API. And these are very, very simple calls. Most of the time when working in a business that's going to require something like a load balancer, you're going to have some services that are very intensive and some that are simple. These are very, very simple across the board since it's just an academic project. So looking at this, we just have a get API, and the get API is simply just going to format some stuff, get query ready, and then we're going to be sending and getting everything and returning those details. Incredibly simple. And really, in reality, it's the same thing with the post. This is, even though there's a couple more lines of code here, there's nothing going on here special. Very simple. And I even threw in a little bit of extra delay artificially, just to give it a little bit more purpose, a little bit more realism, to demonstrate network traffic type delays. Okay, let's go to the fun part. The fun part to me is the actual load balancer. We will start from the controller side of things. So when a request comes through, this is where it's going to come. If you're not familiar with .NET, the way these work is .NET has attributes that can come over these in an API controller. You can see this is an API controller. We are inheriting that controller, and then we have this HTTP GET, which captures anything at the path API / and then ***. Everything at that path with a GET is going to be coming through here. Everything for a post is going to be coming through here, which a post and a GET are all I have. So I didn't need to add like a patch or put, nothing like that. So it's fairly simple what happens in terms of this, because at the end of the day, this is just acting as a pass-through with a tiny bit more logic. And we really want to optimize the logic when coming through something like this, because we don't want to overcomplicate and end up slowing down every request by, a second, or even a tenth of a second. So looking at this, we are injecting into this our algorithm provider. And then the algorithm provider has the current algorithm, and it's going to maintain that. We have the polling service over here. You can see that's going to manage which algorithm is up and running, essentially, as it's polling every 30 seconds. But the algorithm itself is provided, so now we know what algorithm it is. And then the port is defined by the getNext server that's on the algorithm. So let me go to the interface just for a second. So each of the algorithms have a getNext server and an onRequestCompleted, which for connection-based tracking like least connections, we need this onRequestCompleted so that we can manage those connections. So let's go back to the load balancer, the actual controller. So once we determine the port, then all we do is set up our URL, which is hard-coded in this case. Don't do this in prod, please. And then we will set everything up to send that, and things are fairly simple. We're going to just act as a pass-through. We send it, we get the response, we return the response. And we have a finally, which is going to execute at the very end, right? And that finally, that onRequestCompleted, will release, in the case of connection tracking, it's going to release whatever port is there so that we can keep track of how many connections each server has. So now let's tackle each of the algorithms and just briefly explain what they're doing programmatically. So round robin here is very simple, as you would expect. We have the servers here. I considered not hard coding the servers in here, even for the academic purpose, but then after weighing the pros and cons, it seemed to me that it's more helpful to just have it here so that someone who's learning about this can have it like very obviously there, rather than being a bit more obfuscated and coming from somewhere else. So it's very obvious when we're looking here now. This is the server points, the server ports, and then we will essentially just be looping through them and returning the correct port. And the weighted round robin is a little bit different. And this is the one we demoed, where up here we define that config. So we define the weight against the port. So the 3, if you rewind and go back, you would see that the 3001 got 3 requests, the 3002 got 2, and it looked exactly like this, which this is just a simple for each, and then we have an embedded for that does it against the weight so that we're decrementing each time. Next one is the least connections. Well, let's start with the random. The random is the simplest of all the simple. You pick a random number, here's the array, pick a random one, serve the random one, and you're done. And, you know, for being such a simply implemented thing, it is, you don't have to worry about locks, you don't have to worry about kind of a structure, you're just serving a random port, and at the end of the day, the distribution should be fairly equal. And last but not least, the least connection is the trickiest here, but there's nothing tricky going on, really. We have the ports, and then we have the connection counts, and the lock. And all we're going to do in theory, if you look down at the code, all we're going to do in theory is we're going to go through these one at a time and see which one has the least amount of connections, and then serve the next one to that. Now, in our case, 3001 is going to get the most traffic. Why? Because we're looping from 3001 to 3002. So because the traffic is limited in how quickly it's getting there, and these requests fire so quickly, the 3001 can handle a lot of traffic very quickly still. So it's going to go through and do its little for each here and do what it needs to do. And then on the request completed, that is where we're going to remove and decrement the connection counts so that we can manage those against what's needed to make sure the server with the least amount of connections gets the next request. Last thing to show here, if you aren't familiar with it, is the polling service. And in .NET, making a polling service is relatively simple. You just make your class, inherit background service, and then we inject the things we need, which for us, we do need our algorithm provider. We need our HTTP client because we'll be calling out, and then we have the logger. And then going in here, we have this task.delay, which is going to define the polling essentially, set at our polling interval seconds, which up here is 30. So as it's going through, it's going to come down and it's going to hit this API, hence polling, every time, and check against what's configured. And if it's different than what's configured, then we are going to update it. So it will try parse it, see if it's changed. If it's changed, then we're going to try swap algorithm. If you've made it this far in the video, appreciate your time. It's cool doing this little project and happy to share it with you all. And feel free to check out the repo on GitHub. Thanks.